Hello everyone, welcome to yet another video on AG Chemistry. In this video, we are going to talk about a few questions on gaseous state, and the first question that we will discuss is based on faulty barometer. So let's begin with the first question. As you can see on your screen, this is the first question, which reads as: a faulty barometer reads a pressure of 750 mm of Hg when the actual pressure is 760 millimeters of Hg. The evacuated part of the barometer is 20 millimeters long. Calculate the actual pressure when the barometer reads 730 millimeters of Hg. So we have two cases. Here are four options. Let's try and see how can we make the diagrams for the two. So for case 1, when the actual pressure was 760 millimeters of Hg, let's try and mark various data points that we have. So here you have actual pressure is 760 as given here. The faulty barometer reads 750. That means the reading or the height of mercury is 750 here. So let's mark this as 750. So this is 750 mm of Hg. 750 mm of Hg. Then what it says is the evacuated part of the barometer is 20 millimeters long, which means this upper part where there is no mercury filled is 20 millimeters long. So let's mark this as 20 millimeters as length. Now you can see that if this height is 750 and the remaining height is 20, we can mark the total height of the tube, which will be used in the next part. So the total height becomes 20 plus 750 as 770 millimeters long. Now let's move on to our next case. In this second case, the total height still remains how much? 770. So let's mark this as 770 mm, and we are given that we have to measure the pressure of the gas here. Measure the pressure of atmosphere here. What is the pressure applied by the atmosphere? And we are given the reading that we have. The reading in this question is 730. So this part here is 730 millimeters. So let's mark this as 730 mm. So from 770, if 730 is the height of the mercury, the remaining empty part becomes how much? 40 millimeters. So now we have two cases, and we see that there must be some gas filled in the empty part of the barometer because there is an error in a reading, and that is due to the presence of some gas. So there is some gas filled in this empty part, and the same gas remains in this part. What we need to do is find the pressure of the gas here, then convert it into pressure of the gas in second case. And it is very easy to do this. Just let's look at how we'll achieve this. So in case 1, the volume of this empty part will be area of cross section into length, or we can call it as height. Okay, area of cross section into, let's call it as height. So height is 20 millimeters, area we don't know, let's keep it as A. So the volume of gas in this case, for this gas, the volume in first case is area into height is 20 millimeters. The pressure of gas is to be found out, and this can be found using the equation or using the principle that pressure at the two levels will be same in this liquid mercury. So the pressure outside is given as 760, and the pressure inside will be pressure due to gas plus pressure due to mercury. So we'll write an equation that pressure of gas plus pressure of mercury is equals to pressure of atmosphere. Pressure of gas here we don't know, that is to be found out, plus pressure of mercury is due to 750 millimeters of Hg. So we write it as 750 millimeters. I'm not writing the units. And atmospheric pressure is given as 760. So let's put it as 760. So in our first case, what we achieve is pressure of gas is 10 mm of Hg. Volume of gas is area into 20. Now let's come to our second case, and let's do the same exercise here. In this case, the pressure of gas is unknown, that we will find out. The pressure due to mercury will be 730 and atmospheric pressure is to be found out. Volume of gas in this case is 40 into area. So we write here that volume of gas as V2 is area into 40. So area of cross section remains constant and the height becomes 40 for the gas container. The pressure of gas plus pressure of mercury is pressure of atmosphere. Pressure of gas is P2 and that is to be found out. This equation we will keep a note of because this we will use to find the pressure of atmosphere. Now for the gases, what we can do is we can apply Boyle's law as temperature is constant. So let's call this as V1 and this as P1. We have V2 here and P2 is to be found. So using Boyle's law, P1V1 is equals to P2V2. Put P1 is 10, V1 is area into 20, P2 is to be found out, volume is 40 into area. Now if you see, we can cancel out area, this gets cancelled for 2 times and we get P2 as 5 mm of Hg. Now we have pressure due to gas P2, we have pressure due to mercury, which was how much? You just look at the diagram. The pressure due to mercury was 730. So this is 730 mm of Hg. And when you add these two, because we saw in this equation that pressure of gas plus pressure of mercury is pressure of atmosphere. So when you add this, you get pressure of atmosphere as 730 plus 5, which gives you 735 millimeters of Hg. So this is your actual pressure due to atmosphere in second case, and that becomes your answer. Now what you need to see is why do we call this as faulty barometer? So we found out that actual pressure due to atmosphere is 735, but the reading on the barometer is only 730, and that is why it is known as a faulty barometer, because of the presence of some gas in this empty space. So this is the first question. I hope this is clear. If not, just go through it once again. And let's move on to a few more questions on gaseous state, and these are good practice questions. So the next question reads as, volume of a cylinder containing 10 marbles and gas is 1 liter at 2 atmospheric pressure. So this is condition 1. The volume of the container is 1 liter, it has 10 marbles and there is some gas filled in this, and the pressure here, let's mark it here, the pressure is how much? 2 atm. The pressure given is 2 atm. Moving forward, what is given? Now the pressure on the cylinder is increased to 4 atm. So pressure in the second case is 4 atm, at which the volume becomes 725. So V2, sorry, not V2, V2 तो हमने कुछ और mark करा, we have marked V2 as something else. 725 is the volume of the container in the second case, the whole container. Volume of each marble is, the volume of each marble is to be found out. What is the volume of each marble? So what we can do is, we see that the total volume of the container was 1 liter, and let's say the volume of each marble is X. So if we write that let volume of each marble be X ml, therefore volume of gas, which is V1, will become 1000 minus 10x ml. So the volume of the gas that is filled here will be 1000 ml minus the volume of these 10 marbles. So V1 becomes 1000 minus 10x ml. That is what we have written here. In the second case, P1 here we have as P1 was 2 atm. Now let's look at the second case. In the second case, the total volume is 725 ml, and V2 can be similarly written as 725 minus volume of 10 marbles. So this is 10x, this is 10x. So this becomes 725 minus 10x. This is your value of V2. So let's look at this. So volume of gas in second case V2 will be 725 minus 10x ml. P2 here is 4 atm. Now what we need to do is find out the value of x. So we need one equation in x. Therefore, again using Boyle's law, because the gas is conserved, P1 V1 is equals to P2 V2. What we get is 2 into 1000 minus 10x is equals to 4 into 725 minus 10x. If you solve this, you'll get 1000 minus 10x is equal to 1450 minus 20x. Rearranging the terms, you get 450 is equal to 10x, or x is equals to 45 ml. So this is your volume of each marble, and let's see which option it is. So this is your option number B. So let's mark this as our answer. This is our answer for volume of each marble. So this was a fairly easy question. It's just about imagining the situation. If you can imagine the situation, it's easy to do. I hope this is also clear to you. If not, just go through it once again. It shouldn't be too tough to understand. Moving on to our third question. What we are given here is that if pressure of a gas contained in a closed vessel is increased by 0.4%. So pressure is something P. Let's assume it as P, and it is increased by 0.4% when heated by 1 degree Celsius. Then its initial temperature must be. So what must be the initial temperature? We are not given any data here. We are just given the differences. So let's start by doing question using variables. So let pressure initial be P, let's call it as P, and temperature should be T. Now the pressure is increased by 0.4%. So P2 is P plus 0.4 by 100 of P. So this plus the increase is our final pressure, and it is given that T2 is initial temperature plus 1 degree Celsius. And let's say we are writing this in Kelvin. So this is T in Kelvin, right? Or rather, let's do one thing. We are asked to report our answer in degree Celsius. There are options for Kelvin also. So let's do this question in Kelvin only. So 1 degree change in Celsius is equal to 1 Kelvin change in Kelvin units. So the temperature T2 also becomes T plus 1 Kelvin. Now, since the vessel is closed, we can say that volume is constant. Volume is constant, and because the volume is constant, therefore we can write P1 by T1 is equals to P2 by T2. P1 is P, T1 is capital T, P2 is 100.4 P upon 100. So we'll put the 100 down upon 100 T. On solving this, 100.4 P, and this was T plus 1. On solving this, we have P getting cancelled, and rearranging the equation we get that 100 T plus T is equals to 100.4 T. So what we did was we multiplied this, took it here, and we took this T as here, and we got this equation. Let's solve this out. So you have T is equal to T is equal to, just a second, we did a small mistake. This should be 100T. When we multiply this, 100T plus 100, not T. So this is 100. Slight mistake here, so let's correct it. So this is 100T plus 100 giving you 100.4 T. What this gives us is as, writing it clearly, 100 is equals to 0.4 T, and this gives us T as 100 upon 0.4 which will give you T is equal to 250 Kelvin. So let's see if the option matches in Kelvin, or else we'll convert it into degree Celsius. So looking at the question, we get A as the correct answer, 250 Kelvin, because we had options in Kelvin. So your answer is 250 Kelvin. So because the volume was constant, we used P1 by T1 is equals to P2 by T2, and thus we reached at our answer. Now there are two more questions that we would like to do before we end our video. So I hope you will continue with me. Don't take a pause here. Keep solving questions along with me. You can in fact pause the video and try to solve it on your own. If you don't get it, you can look at the solutions and then try it again. Next question. Okay, this is slightly tougher than what we did before in terms of understanding. So the question reads as: a bottle is heated with mouth open to have a final temperature as 5 times to its original value at 25 degrees Celsius. So what we are given here is that you have 25 degrees Celsius initial temperature. We'll convert this into Kelvin obviously. It's heated to 5 times of its original temperature. So T2 will be 5 times of T1. The fraction of air originally present in the bottle that is expelled is, so there was some container, let's call this as AG chemistry container, and let's write also about it. So if T1 was 25 degrees Celsius, or we can say 298 Kelvin, T2 here was 5 times of T1, which becomes 5 into 25 degrees Celsius, which is 100 degrees Celsius, and we convert it into Kelvin. This comes out to be not 100, 125 degrees Celsius, 125 degrees Celsius, and this comes out to be 398 Kelvin. So you have T1 as 298 Kelvin, T2 as 398 Kelvin, and let's say that initial moles present in this container were N1. So initial moles were N1, and because it is an open container, therefore pressure is always equal to atmospheric pressure in both the cases. The pressure in second case is also equal to atmospheric pressure. Now what do we need to do is we need to find the fraction of air originally present in the bottle that is expelled. So we need to find the fraction that is expelled. This is to be found out, how much gas was expelled out from the initial condition. So if we take initial moles as N2 inside the container, and if we take final moles in the container, okay, final moles in container as N2, so what we can do is we have an equation, because if we are talking about the container, the pressure is same and the volume is same if we are just looking at the container. Anything that goes out of container is not in our purview here. So in this case, when pressure and volume is same, we can write that T1 N1 is equals to T2 N2. That product of moles and temperature will be constant. So what we do here is that we write T1 N1 is equals to T2 N2. Why are we doing this? That if we get the value of N2 and we know that total moles were N1, so we'll know how many moles got out. Okay, so let's do this. T1 was 298, so 298 into N1 is equals to 398 into N2, or you get N2 as 298 upon 398 of N1. So this is the moles remaining inside. So how many moles went out? If these were the moles remaining, so what we can say is moles that are going out. Okay, the expelled air has moles that are got out. This is what we need to find out. Okay, this is what we need to find out. So N out, moles out, is initial moles N1 minus the moles that are inside the container still. So initially total moles here were N1, some got out in the form of N out, the remaining are N2. So N2 plus N out is always equal to N1, or you can write this, rearrange this, N out is equals to N1 minus N2. Putting the values, you have N1 minus 298 upon 398 N1. N out comes out to be 100 upon 398 N1. And what we needed to do was find out the fraction of moles that got out. So therefore, fraction will be moles that got out upon initial moles that were present, and this comes out to be 100 by 398, since N1 gets cancelled. N1 upon N1 will get cancelled and you will be remaining with 100 by 98. Now let's see what option can we match with 100 by 398. So we are given options as percentage, and these are perfect percentage, like 25, 40, 50, 33. So let's try and convert this into percentages. So this is fraction. Percentage will be 100 by 398 into 100. Now if you look closely, this can be approximated as 400. And when you approximate it as 400, what you get answer is 25%. So we'll write it as approximately 25% of the fraction, and that becomes our answer. So let's look at the options. Which option is the answer? Option number B is our answer, right? So I hope this was clear. It's not too tough, but yes, it takes slight more effort than the other questions that we solved just before. And to the last question that we are going to solve, and if you keep looking, there is a bonus question. This question will not be solved in this video. I'll leave this to be solved by you, and maybe we can discuss the answers in the comment section or in another part of any other video. Okay, so let's do the fifth question. You must try this. If not, you can look at the solution to understand how we will do this. And the sixth question will be a bonus question. So coming to the next question, fifth question of our series. Assuming that O2 molecule is spherical in shape with radius 2 angstrom, the percentage of volume of O2 molecules to the volume of gas at STP is. Okay, so what we need to do is we have to find out the volume of O2 molecules as compared to the total volume. And we have said that consider O2 molecules to be spherical in shape and radius of 2 angstrom. What we need to do is, let's find out the volume of O2. What is the volume of O2 molecules? So volume of O2 molecules. Now what we know that is that 1 mole of O2 at STP will measure the total volume of the gas, not the molecules. Let's write it here. Volume of 1 mole O2 gas at STP is going to come out to be 22.4 liters or 22,400 ml, any of these. Okay, so this is something that we know. So to find out the percentage, what we can do is, we can find the volume of molecules in 1 mole itself. So what we do is find out the volume of O2 molecules in 1 mole of gas. So we'll have the total volume of the gas and the volume of the molecules, and then we'll find the percentage. So volume of O2 molecules, how do we find this? We multiply Avogadro's number with the volume of each molecule. So you have Avogadro's number of molecules, and volume of each spherical molecule will be 4 by 3 pi r cube. So Na into 4 by 3 pi r cube is something that we need to find out. So Na is 6.023 or 22 into 10 to the power 23, depending upon what value you use, into 4 by 3 into pi into r is given as 2 angstrom. So 2 is 10 to the power minus 10 meter cube. So 2 into 10 to the power minus 10 meter cube. When you solve this, you get 6.022. Let's do this as 22 into 10 to the power 23 into 4 by 3 into pi. 2 cube comes out to be 8 into 10 to the power minus 30, and this is in meter cubes. Let's rearrange the terms. You have 6.022 into 4 by 3 into pi into 8. So these terms are to be calculated together, and 10 to the power 23 minus 30 meter cube. Now you'll have to multiply these numbers and divide by 3. So 6.022 into 4 into pi into 8 divided by 3. If you solve this, this will take some effort, but this value will come out to be 201.8 into 10 to the power minus 7 meter cube. And when you convert meter cube to liter, you multiply it by 10 to the power 3. So this comes out to be 201.8 into 10 to the power minus 4 liter. This is the conversion that we used from meter cube to liter. What is the conversion? 1 meter cube is 1000 liters. This is the conversion that we used. Now, rearranging this into a better number, removing the powers, so you get 0.2018 liters as the volume of O2 molecules, not the gas. Now we need to find out what do we need to find? What are we asked? The percentage of volume of O2 molecules to the volume of gas. Okay. So percentage of O2 molecules volume will be volume of O2 molecules 0.2018 divided by the volume of the gas, which is 22.4 into 100, and if you solve this, you get your answer as 0.09%, and that is your answer. So your answer will be option A, 0.09%. So go through the question once again. If you are confused about any step, this should not be too tough to understand. And these are the questions that I wanted to discuss with you in this video. There's one question which is bonus for you, question number 6. Try it out. I'll tell you what it is based on. It is based on the conversion of pressure. So you'll have to use the relation pressure is equals to rho GH for different liquids, and you compare it with the rho GH of mercury. So you have different liquids here, liquid 1, 2, 3, and then mercury. You will have to convert these heights into height of mercury. So with this bonus question as your self practice, let's end our video. I hope you like the work. I hope this is of help to you in understanding chemistry better, solving questions for various competitive exams. So do keep practicing, keep learning. We'll see you in the next video, and if you get to the answer, just share your answers for this question in the comment section, and I'll revert it back as to what is the correct answer for this question. Okay guys, see you again in next video. Till then, bye bye, take care.